All right, so maybe we can get started. TGIF, once again, another week, another Friday. It's a true pleasure to introduce to you today's speaker, Professor Sanjay Srinivasan of Penn State, where he is both professor and department chair of energy and mineral resource engineering. Uh, Professor Srinivasan, I've had the pleasure of meeting him. I think he reminded me today, many, many years ago when I was a graduate student. And he almost, I guess couldn't recognize me. I was a different person back then. I had a ponytail, long hair, old school.
But you look a lot lighter too.
A lot lighter, yeah. Yeah, that, for sure. Well, Professor Srinivasan, I asked him whether he considers himself to be a geostatistician, still, from the school, of geostatistics, and he replied affirmatively. So that is really exciting for me, and let's welcome him to our seminar. Sanjay.
I've been instructed to turn this on. So thank you very much for this invitation, Rami. It's been 10 years since I came here. And the last time I came here, I presented, I think, 4 doors down, the classroom 4 doors down. And Al Reynolds was there, and Mohan Kherkar was still the chairman of the department. So some things remain the same. But a lot of things have changed. But very, very impressed and very happy to be here amongst so many friends. And so many, I shouldn't say this, they'll take offense, but Jun was a student at UT when I was a faculty member. Rami was a student when I visited Stanford on my sabbatical. So good to be with the next generation and watching them come up too. That doesn't mean that I'm going that old. I'm still young and functioning. But again, I am a very proud geostatistician. Okay, I know that it's a jaded word in the industry nowadays. A lot of people think that all the problems in geostatistics have been solved thanks to Petroleum and all the software that is available. But it is still a very intriguing field. And I'll hopefully by the end of the seminar today, you'll get a glimpse of why I still think there's a lot of things to be done. So the title you see there, mainly looking at naturally fractured reservoirs in hydrocarbon systems, although it can be generalized to sequestration resources and other things. And I purposely put this title slide with the names, and you can see this is where subsurface engineering is headed. You'll be wondering, what is a student who worked with Dr. Srinivasan got anything to do with Lowe's Corporation? You go and buy building materials from Lowe's Corporation, right? Turns out that Lowe's Corporation has a very big data analytics center in North Carolina. And Akshat found his job. He, during his PhD research, he did some very innovative machine learning related things, and that enabled him to find a job in Lowe's Corporation. And Eddie Udekbe, of course, is BP doing classical, reservoir engineering, machine learning for reservoir applications and things like that. So these are the students, and you can see that, we have a very fancy logo. Give it to the students, and they'll come up with very interesting logos. And we call ourselves the Penn State Initiative for Geostatistics and Geomodeling Applications. And it's nicely acronym is P Sigma, right? And if you remember, sigma stands for the standard deviation of the variance. So it kind of fits our identity. So before I get started, the second topic that I'm very passionate about, and I did want to have 3 slides to share with you, is what the heck are we supposed to do when the whole world thinks that we are all villains, right? So somehow petroleum engineering and natural gas engineering and mining engineering, we are the evil people in this planet, right? How many of you feel that perception, right? And so I wanted to share with you. So petroleum engineering education in a post-COVID world. Anybody who is a rational engineer, scientist, modeler will tell you that energy transition is not going to happen overnight. You just flip a switch on and then suddenly you are into renewables, right? So natural gas, of course, is going to play an important role. Even if you go with renewables, things like critical minerals, getting critical minerals from produced waters, from subsurface sources will remain a big issue, right? Right now it's dominated by one country, but those resources have to be more globally accessible. And so there's going to be a demand for those kinds of people. Geothermal energy production, if nothing else, when people say geothermal, oh, I'm living in the cold part of country, geothermal has got no application to me. Well, geothermal will always help you with district heating, those kinds of things. It need not be all for power generation, but at Penn State, we are not in geothermal country, but we are advocating deep geothermal wells for campus heating, right? And it's a very viable thing, and petroleum engineers are trained to do those kinds of things. Sequestration, of course, you have heard, if coal survives, if natural gas has to be a viable form, sequestration is going to be a big thing. Nothing else. If you are like me, I grew up in the 80s and I grew up in India. You write a big entrance exam, and it's called the IIT entrance exam, Indian Institute of Technology entrance exam. You take that exam, you pass, and if you pass, you naturally go to computer science. That's the only field Indians think about, computer science. Everybody en masse computer science, right? And I passed that exam, and I said, wait a minute, what the heck? There must be something more interesting. And somebody talked to me about, hey, can you imagine a petroleum reservoir 7,000 or 8,000 feet? At that time, that was the drilling depth, 8,000 feet below your surface, and you're trying to predict recovery. To me, that was fascinating. Hopefully, that will remain fascinating. Those challenges will remain, whether it be for predicting earthquakes. Dr. Rami is working on earthquake predictions and things like that. So innumerable challenges, right? If nothing else from a scientific pursuit standpoint, I mean, and I make that case that, it's an interesting field. Let people understand what the challenges are and the high tech that goes on in these fields, and then we can see. But I do advocate for changes, and this gets me into trouble always when I present this to petroleum engineering community. You cannot be teaching reservoir engineering from Kraft and Hawkins, which you've been doing for the past 40 years. You cannot keep doing that. Right? Yes, that's going to be important, but you need to mix it up with other things. You need to teach students about life cycle analysis, right? Cradle to grave type analysis. And then how do materials transform, right? And things like that. Those are very important concepts. You need to have immersive capstone experiences. Gone are the days where you could do a small petroleum project, or you have initial wells, you do the exploration, you come up with design, make it bigger. Is there a scope to build in renewables? What else can you do, right? With your development, what interesting financing models are there, right? And so those are going to be important concepts that can be learned through integrated capstone experiences. Now, I'm glad to read, I only chanced upon it yesterday, that you guys have launched an externship program, which is great, right? That's the way to engage with the industry. You foster creativity and innovation and professional growth by harping on these externships. I'm glad that TU has done it. We have been trying to do it for some time, and it's going there, it's getting there. So the challenge is, of course, you guys know this. Some of your students will not know this, but the faculty would know this. We have 130, 132, 134 course credits. We have to fit it under ABET. And ABET says you have to teach this, you have to teach that, you have to teach this. So we need to be very, very creative about how do we advance some common core engineering curriculum. The university, I don't know if it happens at Tulsa, Penn State will insist that students have to take philosophy, general education core. In the midst of all that, we need to fit some other modern things like decision analysis, risk analysis, engineering and environmental ethics. These are good common core concepts that every student should be educated with. So how do we do that? One thing which is very fascinating to me, Tom Blasingame, who was the former president of SPE, visited us, and I got him in touch with the president of AICHE, who happens to be at Penn State. And we said that, why don't you guys come together and develop course banks in conjunction that can be shared? So I don't have to develop a specific course on data analytics, predictive data analytics, if it exists somewhere else. I don't have to waste my instructor resources if I can leverage on others, right? If Dr. Rami can teach a course on high fidelity numerical simulation, and I can send my students online. Nowadays, everything can be done online, asynchronous or whatever. That's the way to leverage, all of us coming together and offering curriculum. And then, of course, this integrated capstone experience. We have started. I don't know if you are aware, and it's not yet late, and I would encourage the faculty. There is a design competition that DOE has launched, right? They want a team of students to look at technologies that have been developed in-house at DOE, evaluate those technologies, and come up with a plan to market and make those technologies more popular. There are some very cute ones there, some very interesting ones that we wish it could have become more popular, right? And so we are forming 2 design teams. It involves a lot of engineering, a lot of financial modeling, a lot of life cycle analysis. So bring the whole lifestyle together, and if you win accidentally this DOE competition, you are richer by $250,000. That's the prize money, and it brings a lot of reputation to your institution if you win, if you do well, right? So there are some interesting things you can do, and you have to present. You need to do your elevator pitches and all those things, which is interesting. Okay, so I just don't want to bore too much, but this is something I'm passionate about. That that we can come together and we can do some interesting changes. So now let me launch into my first part of my presentation. This is work done by Akshat. Akshat graduated in September last year, and we started this off as a pure geostatistical modeling type project, and then very quickly realized that, hey, there might be some interesting possibilities to bring in some geomechanics into the model, right? And in the process, bring in some machine learning and things like that. So again, please don't mistake me. I am not offering the solution to all the world's problems. These are interesting perspectives seen through my eyes. Some of them might already exist, but still it's very new to me, and I'm passionate, I'm excited about it. So, of course, I don't need to tell you fractures. You need to have a good handle on fractures to predict performance and production potential. If you're doing unconventionals, knowing where the natural fractures are, it's very critical for designing your stimulation strategy. Well placement, field development decisions are crucial, are guided by knowing your knowledge of fractures. And then financial and investment decisions, right? And nowadays there's a lot of attention placed to things like early breakthrough, produced water handling. Those kinds of things require you to have a good handle on your fracture network. Again, if you are talking about this to a geophysical audience, I hope there's no geophysicists here. Geophysicists can see everything in their seismic volume. They can see channels, they can see fractures, they can, So to them, I say, okay, let's have a side conversation later, right? The fact remains that there are some mysteries of the subsurface that are not easily visualizable, right? High resolution seismic, despite the availability of that. There have been a lot of people working on fracture characterization. Golder Associates every year produces at least 3 revisions of their software. Mark McClure, who graduated with Stanford, I don't know if Rami graduated with him. Was he after you or before you, or around you? After you. So he has his own company, right? And he has his own interesting way of modeling discrete fractures or flow in discrete fractures and things like that. So a lot of people working in them. But I would argue that a lot of things that they do is not, geologically realistic. Now, there are some. I have a very good friend of mine at Carnegie Mellon, and we collaborate. They look at fractures as basically, art or manifestations of deformable media, right? So think about crumpling a piece of paper and all the planes of discontinuity that arise. So treat fractures like that and come up with all the mechanics modeling. Very nice, very elegant, but very cumbersome material for 5 PhDs, which companies are not going to really take on, right? So we wanted to be simplistic, but at the same time be geologically realistic. Insufficient data for field scale modeling. And then you need the algorithm to be flexible enough to incorporate seismic data, production response, and things like that, and consider whatever uncertainties that are introduced because of that data assimilation process, right? Now, if you pose this problem to a classical geostatistician, right, and there are many of them, brilliant people, Jean-Paul Shields in France is one of them, specializes, his entire life is devoted on fracture modeling. And he is I mean, I don't know if Rami, you know, or anybody here knows, a brilliant mathematician, absolutely top-notch, okay? But the way they model it typically is using something called, I mean, most of you know this, you know, a 2-point correlation measure or a semi-variogram, right? So patterns of variability are captured through this 2-point statistics. And the uncertainty is depicted using multiple realization, right? Generate an ensemble of fracture models, and through that, make some statement about what the uncertainty is. And of course, these models can be conditioned to orientation information, fracture length distributions, all those kinds of things, right? And I'm showing you a typical variogram for those who are not familiar. It's measuring how correlated are 2 points in space separated by a lag h, right? Lag, a distance lag in a particular orientation. So Mohan Srivastava, who is Andre Journal's, one of his, you know, Andre calls him his gem, right? The star, right? And Mohan is a brilliant guy. And so Mohan and I got talking at a Geostat Congress in Oslo, I think 7 or 8 years back. And Mohan's knack is simplifying the problem. Simplifying the problem, but making it look beautiful, elegant, very elegant, right? And I know, I bet you must have met people like that who can take a very complicated problem, but write it and express it in a fashion that you say, wow, I never thought about it this way, right? And you had one, you know, I always thought Dean Oliver was one of those kinds of people, right? And you know, he was a faculty member here, and there are others. I mean, no disrespect to anybody else here. Okay, so Mohan is one of those people who can simplify a problem. So he said, okay, I'm going to apply 2-point geostatistics, but I'm not foolishly going to use 2-point geostatistics to simulate a map of fractures. Rather, I'm going to use the 2-point statistics to guide the propagation of a fracture. So at the fracture tip, I will look at my surrounding data. I will do like a Kriging or a sequential Gaussian simulation. I'll get a probability distribution. I'll draw an angle from that probability distribution. And based on that angle, I will propagate the fracture of finite length in that orientation, that direction. Very elegant, right? I mean, classically, geostatistics was always done on a gridded domain. Right? You take the conditioning data and you create a map. And Mohan said, no, why? We'll just focus on the fracture tip and propagate. And so he's doing a Gaussian simulation on geometric attributes. So it becomes a propagation type modeling. And so here is an example, a picture of this. So I'm showing you some blue filled nodes. These are existing traces. You know them, you know the fracture traces. And then you have some nodes where you're trying to simulate the fracture. There's open nodes that I'm showing you here. These are the seed nodes, right? And so you start doing the simulation. You go to the fracture tip, one of these white nodes, the open nodes. You look at the configuration of the surrounding data, and then you do a Kriging or a sequential Gaussian simulation conditioned to the variogram, the pattern variogram, right? And then depending on the Gaussian simulation and the value you draw, you propagate a fracture in a certain orientation. Now, of course, you know, the way Mohan proposed it is that you also take out some of the nodes from the traces and you resimulate the traces just as a calibration check, right? And then you can fill out the rest of the pattern. So I'm showing you the remaining patterns over here and the existing trace in black, and these are the simulated fracture patterns over here. Okay? So Akshat started working with that, and he said, okay, first problem I run into is that I need to separate the fractures into chronological sets. What came first, and then what came later, right? Some fractures in the original set are positive angled in terms of angle to the azimuth 0. Some of them are negatively angled, right? And so we do need to separate these apart. Otherwise, the mean angle for positive and negative will be a 0. So all fractures will be straight lines along the east-west direction, which is not what you want. right? So in order to create the complexity, you need to separate the fractures, model each of those chronological sets separately, and then put them all together. So he did that, right? And so, orientation was known, intended fracture length was known, and then you need to simulate whether a fracture is in a chronological set 1 or chronological set 2. And so, you have some conditioning data, which I'm showing as stars, and then the open nodes are the seed nodes. And then you start the simulation process. After 2 iterations, this is the kind of map that emerges. And then finally, you get a pattern that looks fairly similar, not exactly similar to what the variogram statistics was obtained from a synthetic image like this, and the final simulated image looks sort of like that, right? I mean, not exactly, it'll never be exact because of the lack of conditioning, but fairly similar, right? Fairly similar. So all happy, very good, but the problem is you have to do this chronological separation up front. And if you sit down with the geologists, they will take a microscope and they will look at the quartz cement, and then use the cement to date the fractures, and then model the fractures in chronological sequence. It's very awkward, right, from a modeling perspective. The second thing is that in this image, you see that some of the fractures are through going, some of the fractures are sort of terminating, not exactly, they're sticking out, right? So you do need to give some sort of termination rules. Right? If you want to make it look exactly like the image where the fractures are beautifully terminating against existing fractures, against apparent fractures, you do need to give termination rules, and you have to somehow come up with termination rules. And Akshat employed a certain termination rule to make the images look the way they were. So we said, okay, let's try and see if we can extend geostatistics to handle some of these issues. And so we said, okay, multiple point statistics. Let's see if you can apply multiple point statistics. Stanford developed this. Srinivasan Mohan was the original author of multiple point statistics, but it has come a long way beyond what Mohan really proposed. So we said, okay, the beauty about MPS is going to be we don't have to come up with any termination rules, because the termination itself is a pattern, and you can learn the pattern, right, from whatever data that you may have, the training image is rich enough. Secondly, you don't have to apply any kind of termination rules, because the termination is happening, and you don't have to do any chronological sequencing of fractures, because for me, a fracture is a pattern. I don't need to distinguish between what came before, what came after. I'm going to just simulate the pattern, a fracture terminating against or intersecting a fracture and continuing and things like that. So ideally, the MPS should be able to capture whatever termination, truncation I'm seeing in the training images and things like that. Now, there is a whole question about where do you get these training images? Let's not get into that, okay? We have some ideas about that, but that'll be another lecture. So I have, it was not new. This work started, when I joined University of Calgary. Xiaohuan Liu was a master's student who started at Calgary in 2003, just when I was in the process of transitioning from Calgary to UT Austin. So Xiaohuan moved with me, and we had come up with this thing. And we said that we are going to be smart in conventional. How many of you have heard multiple point geostatistics? Anybody here? No? So what you do is, I'll give you a 20-second round trip here. So you have a template, a spatial template. Right? Is there a marker pen or something you can borrow? I'm a university professor. I'm allowed to write on the board, right? I'm allowed to write on the board, right? I mean, what is life without writing on the board? Nope. Okay. I have a cap, but not the pen. But that's okay. Okay, so let me hand wave. Okay, so imagine, so a variogram is 2 points in space. Okay, 2 points in space. How do you infer a variogram? You must have heard of a variogram, right? You have a geostatistics class, right, Rami? Yeah. So you've heard of a don't lie. Semi-variogram you've all heard, haven't you? Okay, let me start with the story then from ab initio. So 2 points, you take 2 points separated by a certain lag in a certain orientation. You have a domain where you may have some data. You take this template and you translate it over the entire domain. Hopefully it works. Thank you. You translate it over the entire domain. Every time when you put a point at the template at a certain location, you pick up the tail value and the head value, right? And you can create a scatter plot. A scatter plot of, see, all universities are all the same. Penn State, out of 100 markers, 2 will work. Right, so this is the tail value, this one, that's the head value. So the combination of these two becomes a point on this plot. And then you translate this template all over your domain and you create a scatter plot. Right? And then you compute the moment of inertia of this scatter plot. Right? You draw perpendicular bisectors, take the distances, square the distances, that's how you compute the moment of inertia. Right? So when you finish doing that, remember that variogram plot, that gives you 1 point on that variogram plot. Then you do this for another template, a little bit wider, and you get another point. A little bit wider, you get another point, and that's the variogram. That's your variogram, right? So it's 2 points translated over the entire space. So in MPS, multiple point statistics, you generalize it. You say, rather than 2 points, let me take a template. It could be a template like this. It could be a template like this. Right? And I take this 4-point template and I move it around my image and I keep track of what's happening here, 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 here. So if you want to generalize this, I can plot a 4-dimensional plot, right? Because there are 4 nodes, 4-dimensional plot. But then I also keep track of what's happening at the central node, right? Even the 4 nodes are doing something, what is the outcome in the central node? I keep track of that too. Now you can imagine if I have a reservoir with only a few points like this, every time I put this template, I might not find 4 points that line up along these locations. So that's why when you do MPS, you need a full training image, an image that where you have information everywhere on a grid, so that when you move the thing, you can pick up all the variability because the grid is full of information rather than just a few points in space, right? So that was what, and then so what do you do with this? So once you've done this, just like a variogram, you can think that you will have some sort of a histogram, and that histogram is called multiple point histogram. It's basically saying that this pattern, high, high, low, low, this pattern has this frequency of occurring. Another pattern has this frequency of occurring. So that's what the multiple point histogram is, right? So with this multiple point histogram, you start your simulation. You go to an empty reservoir model that you don't know anything about. You have a few conditioning data, and then you visit this node over here where you don't have data. You put the template, and then you pick up, oh, there's 1 point here, there's 1 point here. Based on my histogram, this is the probability of this outcome at this location, right? And so by doing this systematically over the entire domain, you can create a nice looking reservoir model that has got all the features that your training image has. That's MPS. Why did I go through all this long story? Not because I want to give you a class in geostatistics, right? Because in this traditional geostatistical workflow, I am simulating the outcome in the central node given the outcomes in the surrounding nodes. That's what MPS does. Right? So I go 1 node at a time, I put the template, I look at the surrounding nodes, and depending on that, I put the value here. And then I go to the next one and do that. And think about it. That's so inefficient, right? Because, why is it so inefficient? Because what I'm trying to simulate is a feature, a spatial feature. A spatial feature is not defined by 1 node. It's defined by a sequence of nodes. So Shahwan's brilliant idea was, why are we doing this in the conventional MPS framework? Why are we not growing patterns conditioned to patterns in the surrounding nodes? So he called his algorithm, gave it a very fancy name, Growth Sim. We presented this algorithm at the Geostat Congress in Banff. Rami was not a student yet. And the Stanford people hated it. Someone other than their Stanford lot had thought about an algorithm that was different. And I know Andre's face went red and he's, oh, they're never going to work. Never going to work. Right? Yeah, Andre is my advisor too, so he's a good friend, but you know, when it comes to academic competition, it can be friends and brothers don't come, right? But Shahwan did this, and he said, and he came up. You can see that, right? And this is the training image on the left I'm showing you, and then he applied this algorithm, this growth sim algorithm, and the image simulated. Of course, remember, no MPS, no geostatistics can really simulate the aperture of the fracture. Those are, subgrid scale. So you can at the most get the pattern and then fill the aperture from drawing from some distribution. So don't worry about the intensity of the lines, but the pattern looks fairly similar, right, from what I'm showing you here. But we were not very happy, right? Another student came, a Turkish student, Selin Erzebek, and she said that it doesn't make sense to simulate fractures on a grid at all because of the aperture problem, right? Apertures are of the order of millimeters. Your grid blocks at the minimum are a size of meters. How can you ever simulate a fracture on a grid? Because the fracture is a subgrid type element, right? So she said, forget about any meshing. We will directly simulate fracture on a gridless basis. So we will not worry about, this is coming back to Mohan's idea, right? I'm just going to simulate the fracture, forget about the grid, the surrounding grid, and things like that. But then she said that very smartly. She said that I'm going to have a problem always if you're going to tell me that I need a full exhaustive training image to get the statistics. Because you're never going to get that. Look at this. This is a Wagon Cave outcrop somewhere in the Utah, Wyoming area. And you can see that all that you have are fracture traces, or actually in this case, these are caves, right? Karstic caves. You only have the trace of the caves. That's all you have. You don't have any surrounding information on the grid and things like that. So she came up with an algorithm and she said, okay, I'm going to take a template, but I'm going to use a variogram by giving some tolerances for the lags, because no 2 points are exactly going to be that far apart in that orientation. You always give yourself some tolerances. So same thing I'm going to do. I'm going to infer multiple point statistics, also give myself some tolerances to infer the statistics. So that was Selin Erzebek, and she did this, and she did a kind of a hierarchical simulation and things like that. Very, very nice work she did. And she could come up with fracture networks that have the complexity, right? So the good thing about what she did is that she tried to do this on multiple scales. Like, let's get the small cave segments, let's get the large cave segments first, and then let's start infilling the features for the smaller scale features and things like that. So some interesting things she did. So Akshat got this, and he said, that's also not very good. Right? Every student has to disprove what the earlier student did, right? That's how you get a PhD, right? And so Akshat said, oh, this is not very good. Why? Well, because Selin had to use some templates. And those templates, how the heck do I know what will be the optimal template to reproduce a certain pattern? I have no idea. I would like the template to evolve as the simulation progresses. I do not have to be giving the same template, the optimal template up front. Rather, let the algorithm learn what the template should be, right? And then the second thing is that I want the scheme to be such that, I told you, Selin did the large scale simulation first and then started infilling the features. So Akshat's point was, I should not be doing that. The algorithm should be infilling features or doing the multi-scale modeling automatically without really. Yeah. So along comes our friend Gregoire Maritos, who's a faculty member at Neuchâtel. He was a postdoc at that time. Now he's a faculty member in Neuchâtel. And he came up with this algorithm called direct sampling. Right? So in direct sampling, if you think about this algorithm, when I'm doing the simulation, I have to first compute this entire histogram. Then when I'm doing the simulation, I look at the pattern, and then I look at the histogram, and I draw a value and put it over here. But the computation of this histogram takes an enormous time. In fact, there are many people, Strobel, Strobahar, all these people, implementing search trees, implementing whatever. I don't even know what the stacks. You guys are computer physicists. I don't understand that language, right? So all kinds of schemes they have to think about, how to store this histogram, scan it, and then reproduce and all that. So Gregoire said, forget about this. I'm going to go in my simulation, whatever the pattern is around my surrounding nodes, I'm going to search my training image. The first time I see that pattern, I'm going to apply it. I'm not going to bother constructing this histogram at all. First time I see a certain pattern, draw a value, go on. So it saves the trouble of going through and constructing a histogram and all those things. So direct sampling, if you go, how many of you are thinking of doing a summer internship? If you go to a Chevron or Schlumberger and you say, I know what direct sampling is, your prospects go up 25% because it's an in thing. Everybody's talking direct sampling, direct sampling. Everybody loves Gregoire. Gregoire is a superstar. He's the Abba of geostatistics, right? So Akshat said, oh, this is going to be an interesting thing. Because in Gregoire-Maritoz's algorithm, you do not have to pre-specify a template. The template gets chosen as you're doing the simulation. You're looking at the surrounding nodes. Whatever the pattern is, that is the pattern I'm going to pick. So I don't need to specify a template at all, right? I don't need to compute these multiple point histograms, and I can simulate the propagation angle. So again, Akshat, in his mind, I like Mohan Srivastava's algorithm of propagating fractures. I don't like the fact that he's propagating condition to variograms, and then I have to split it into hierarchy of fractures and all that. Let me borrow multiple point statistics. Let me use the direct sampling algorithm that Gregoire had came up with. So here is an example. This is the Valley of Fire outcrop in, I think it's in, I'm embarrassed. I think it's in Utah. It's in Utah, right? It's a basement features. You can see you can actually walk along the fractures. So this is the network that you see. Of course, when you squint very hard, you're missing some things over here because there's also some topological folding and things like that. So Akshat came up with an image processing algorithm, and he said these are some of the main features. Of course, you see some artifacts that are coming up and things like that. Okay. And then he said, okay, I'm going to do this multiple point statistics based algorithm using direct sampling. I'm going to look at the surrounding nodes for what orientation they have, and then I'm going to start simulating. The only thing he saves in memory is some angle, some orientation distributions over the entire fracture sets that you have in the training image, what orientations you're seeing, and what the total approximate length distribution of the fractures are, and things like that. So he starts the process. He puts he starts simulating. No template used, right? And there, he's showing you that there are some yellow nodes that are the conditioning nodes, and then the red nodes are the simulation nodes. So at every step of the simulation, he's looking at the pattern of the surrounding nodes, and then propagating the fracture according to the multiple point statistics that you draw from that thing. So again, of course, you realize that when you start looking at the surrounding nodes, the pattern of nodes may not exactly match the pattern in your training image, right? Because you may have, when you're at a particular node, you may have an angle, certain angle between the nodes, and when you search the training image, those angles may not be preserved. So you need to give yourself some tolerance for inferring the statistics, just like Celine Erzebek did. And so Akshat also did that, gave himself some tolerances to be able to extract the information, and then applied this direct sampling algorithm. I got the paper here, Water Resources Research, right? Gregoire-Maritoz. See that the simulation looks great. No termination rules have been prescribed, but you can see that there are some nice terminations, some nice intersections. All those things automatically emerge because you're inferring these pattern statistics and things like that. And he's showing you the reproduction of the histogram angle statistics. There's almost no difference between the two images in terms of overall angle statistics and things like that. Of course, when I present this, if people want to criticize, what are they going to say? Don't tell me these images look the same. You got to prove to me that they are the same, right? So, okay, Akshat, you need to do some flow kind of modeling. So he came up with this thing. He said, okay, I'm going to transform this entire image into a graph with vertices and edges. I'm going to launch some random walkers through those graph network and look at some arrival statistics, right? And so you can see the blue histogram is the arrival statistics on the actual image, the training image, or whatever the reference he chose. And here is the one that on the simulated image. They're very similar. They're very similar. Of course, I was not going to let Akshat graduate just with that, right? You always have to give them a little bit more to do. So I said, okay, Akshat, but I can argue that you're borrowing all this just based on pattern statistics. If you present this to a physics-based audience, they're going to say, where's the geomechanics? Fractures propagate because of paleo stresses and things like that. So where is the geostatistics? Where is the geomechanics? And so I said, okay, can we now think about bringing in some geomechanical information and things like that, and recognizing that prevailing boundary conditions and local stresses play a role, and also recognizing, I'm a big fan of geomechanics, although I don't claim myself to be a computational methods. Rami is a much better computational modeler, right? They do fantastic things in geomechanics, right? A lot of beautiful things. But then when you ask them to simulate, they'll simulate a fracture pattern on a domain 1 meter by 1 meter. And my valley of fire is approximately 92 square miles. So forget about doing anything on that scale using a pure. Of course, he has very smart ways of doing the surrogate modeling and all that, and we can talk about it later. But pure geomechanical codes, have trouble on working on that scale. And then, of course, selfish motive for me, I had no idea about machine learning. Akshat, let me learn a little bit about machine learning through you. Right? Let me learn a little bit about machine learning. So let's try and see if you can apply machine learning to infer some rules about fracture propagation from geomechanical simulation. So we're using machine learning as our reduced order modeling tool, right? That's what we're doing. Of course, so Akshat did that using a variety of tools. Of course, he would every week he would go away and he will implement something and come back. I'm like, you cannot be coding that fast. What the heck? I did not. I'm a naive guy. I did not know that PyTorch had modules for everything. Everything under the sun you can do with PyTorch. How many of you use PyTorch? Right? You can do everything in PyTorch. You have a module for everything. So that's something I learned. I thought, this guy's super, man. This coding every week he's coming up with an answer. This is amazing. I didn't realize that he was using standard routine. So then we decided that, yes, all these methods have their own strengths. So we are going to use a voting classifier that combines the results from all of these machine learning tools in order to infer the rules for fracture propagation. But of course, all these tools require a training set. And so the training set, the model that we use to develop the training set, many options exist. McClure's code is there, many things. This was my humble effort to reach out to DOE and ETL. Actually, Los Alamos has this code called HOS. And we said, okay, we'll use HOS. It's supposed to be doing all kinds of funny, fantastic things. We'll use HOS, recognizing that it is for brittle materials, not for poroelastic materials and things like that. Just for a demonstration, we wanted to say, okay, let's do it and see what happens. Right? So we used HOS, FDEM, to do this thing, high fidelity simulation software. And so we ran this software for various combinations of displacement boundary conditions, stress boundary conditions, flaws at different locations and things like that, just to verify that it gives something that we can use. It shows some nice branching and things like that. For some reason, we could not get this software to do hooking and things like that. If you are interested in those kinds of features, I don't think we were able to reproduce that. Maybe there's a trick in HOS to do those. I wasn't aware of that. So we are going to use a machine learning algorithm. So we need to do some feature extraction. So we said, okay, let's take the normal thing. We are going to run the FDEM software. We are going to keep track of how far we are away from the boundaries, what the stresses are at the boundaries, and then what is happening to the angles of fractures in surrounding nodes. And we have a classification scheme for angle classes and things like that. Right? So angle of initial flaw, angles of the flow of flaws of the closest 4 fractures. So remember, we are trying to do the training, right? We need to have some predictor variables, and then we're going to predict the angle of propagation of the fracture. So I show you different things, different features that we extracted. And then you run it through a random forest, for example. You're doing a classification problem. Is the fracture in this angle category 1 or 2 or 3? So instead of modeling the fracture angles as a continuous variable, model the angles in classes, because it makes the problem a little bit simpler, right? Because otherwise you'll have to do a regression after doing the classification and all that, just to avoid all that. So decision random forest would look like this. And then he looked at the feature importance and things like that. So after all that, here is the image you get when you start propagating fractures based on some probabilities inferred on the geomechanical simulation. Again, looks fairly reasonable, right? There are truncations that you see, some fractures are intersecting. Again, the arrival time statistics look to do very well, things like that. And then the geostatistician in me creeps up and I say, you know, you did all this geomechanics. It is for homogeneous material, brittle material. There's always going to be some uncertainties with your fracture propagation. So can you think about how to merge the probabilities you inferred based on geomechanics with the probabilities that came from the MPS, the pattern-based simulations that we did? So let's try to merge the two things. Then we are in the happy world that we are getting information from both sources and things like that. And so for that, again, going back to my advisor's work, 2002, the last piece of work that he did before he retired and started composing poetry. So he came up with this very elegant approach for merging probabilities. Right? He calls it the permanence of ratios. Simply put, what it is that you compute these what are called odds ratios. What is the probability of an event not happening relative to the probability of that event happening? Right? So when you see this P theta hat is the event not happening. So it's a relative ratio. It's a ratio of an event not happening, probability of an event not happening to a probability event happening. So it's the logistic type ratio. So he defines these logistic type ratios for various probabilities. This is the prior probability of an angle. Before I know anything about geomechanics or pattern statistics or anything like that, just simply based on angles that I've read from training images, this is my prior understanding of what the fracture orientation should be. B is the information that I'm deriving from multiple point geostatistics, right? So based on the pattern statistics for value of fire or whatever it is, this is the odds ratio that I'm computing. And this odds ratio has got a very interesting interpretation. If I know that the event B is guaranteeing that the event theta would happen, an angle should happen, then this odds ratio will be 0. If it guarantees it should not happen, then the odds ratio will be infinity. So it's like a distance measure, a relative distance measure, distance to an event happening, right? So odds ratios. So again, you can compute an odds ratio for the geomechanics, you know, the information from geomechanics, you can compute a C, right? And then you merge them. And this is where Andre's genius, right? He said, okay, I'm going to say that the ratio of the information that you derive from these things is going to remain invariant whether I take the ratio x to b or c to a. Right? That's the permanence of ratio hypothesis. And there's a theory about it. Those of you who dabble in statistics will say this, look at this and say, oh, this is like conditional independence. It's not. Andre in his paper will prove that it's not really conditional independence because we are talking about independence between odds ratios. It's not independence between probabilities, okay? And then he brings back dependence between events B and C through a parameter he calls tau. Right? Tau is an interpretable parameter. It's a very difficult parameter to evaluate. That's the flaw in Andre's paper, that he doesn't give you any recipe to compute this tau. The redundancy between information coming from geomechanics and geostatistics, the tau, how to get it, he just stops short. He doesn't tell you how to get it. Okay? So poor Akshad, I told him, we will, not right. Hush, hush. Don't say this to the math community. Let's use this tau as a kind of a dial, right? So we are going to dial in the tau, looking at what the training set is doing, and then use the tau to get the image that you simulate closest to the training image. So we are using this tau like a freedom parameter, like a history parameter, history matching parameter. Okay, not a good approach. Pardon me for that, but we are engineers. We do with what we can. So application, this is the teapot dome. This is a different dome. How many of you know about teapot dome? There's a whole story about it. This was a DOE sanctioned project, right? It turned into a scandal. If you go into Google and type teapot dome, there's a whole scandal about teapot dome, about data that was done and some insider things that happened and all that. So this is the data set is available. If you are doing a field project, brilliant data set, everything from 3D seismic, well logs, FMI logs, everything is available. Everything is available about this teapot dome, okay? So this is the pattern, and this is from a thesis, PhD thesis of Cooper. Hey, Rami, you need to keep, I'm a professor, I can talk for hours, so you need to keep me on time, okay? So this is the fracture network, okay? That in this thesis that he talks about. And there is some other thing about Cooper. You know, in Cooper's thesis, he came up with the fracture pattern, and a later guy, Schwartz, came about. He looked at the FMI log at a particular location. And he said, "What is this Cooper guy doing? The fractures that I'm seeing at this location is completely different from the one that Cooper has." And so Akshat's premise was that really, if you want to reconcile the data that came from both this Cooper guy and the Schwartz guy, you need to merge the geomechanics and the geostatistics. Otherwise, you'll not come up with an explainable model, right? In his thesis, Akshat makes that point. So he said, oh, this is a prime candidate to demonstrate my algorithm. So here is my training image. I start my simulation. I'm going to be guided by the combined probability that I infer based on permanence ratio from geomechanics as well as from geostatistics in order to populate the fractures. And so the final simulated image he gets is the one that I'm showing you over here. Right? He gets a final simulated image, the red lines of the fractures. Unfortunately, I should have pasted both of them alongside each other, but I didn't. Sorry about that. But you know, again, I can show you the connectivity statistics, and hopefully, as engineers, that comforts you. The histogram of arrival time of random particles is about the same for both the networks, indicating that the connectivity characteristics are adequately captured. Not perfectly captured, but adequately captured. Okay? All right. So that's the first part of the story. Alongside Akshat, there was another student, Eddie Udipe. And through Eddie, we were interested in a slightly different take on fractures. So you are all reservoir engineering students. You have taken reservoir engineering, right? Some of you. So as reservoir engineers, what is the one piece of information that you have a lot of faith in, that you use to infer about reservoir characteristics? What is that one piece of information? Production data? Production data, right? We live by production data. We don't realize that we have very few wells, but we still production data. That's the gospel truth, right? So we wanted Eddie to look at that, say that, okay, given some production data, can you infer from the production data what the characteristics of fractures in the vicinity of a well would be, right? It's a difficult problem, but Eddie was an electrical engineering student, right? And he was into signal processing and things like that, and he wanted to get into that. And so basically, he posed the question as a big data analytics type problem. Right? I have a lot of data over time, very sparse in space, but using that time intensive data, can I assess something? Can I say something about the near wellbore fracture characteristics? Right? And he presented an SPE paper, and we wrote a journal paper about that, but that's not what I'm going to talk to you about today. I'm going to talk to you about Eddie's application of the same methodology, but to infer spatial patterns of fractures from seismic data sets, because the title of this talk had seismic, right? And so I need to talk a little bit about seismic. So this is an interesting algorithm. He says that I'm going to extract the features in a spatial data set or a temporal data set using some simple, very simple to compute, descriptive data-derived attributes, right? Some very simple attributes. Now, of course, these attributes are so simple that by themselves, they're not going to tell you much about the spatial characteristics. So I need to intelligently combine these simple statistics that I derive from multiple sources, right? And so for that, I'm going to use all the machine learning or the data analytics machinery, adaptive boosting and things like that, and then use that trained the algorithm to detect fractures very quickly from seismic data sets. So that's the algorithm. Okay, so simple template, simple statistics, have a scheme to combine the statistics using some adaptive boosting. Once you're finished training it, apply it on a seismic data set to say where the fractures are. Okay, so this is based on, you must have heard this, it's a Viola-Jones phase detection algorithm. This is the algorithm that they started using first. Now, of course, there are a lot of refinements. Initially, when they were doing this, walking through the camera on an airport and then recognizing who you are and spotting you and making you go stand in a line and strip and search and all those things. This was this Viola-Jones detection algorithm. What is the beauty about this algorithm is that feature extraction is based on very simple Haar-like features. Haar-like features means, you can look at it over here, right? It's a template, but here the template is the contrast between the black regions and the white regions. Right? What is the contrast? Here it is a vertical stripe template. So what is the contrast from black to white to black, right? So if you think about it, this is looking at some sort of a gradient information. This is looking at some sort of a curvature type information. Without explicitly saying anything, those are what these Haar wavelets, Haar-like features are really capturing. So I'm going to try and use these Haar-like features, derive some classification based on each of these Haar-like features, and then combine them using this adaptive boosting. Once I finish training, deploy it on a seismic data set. That's what I'm going to do. Right? And this adaptive boosting is very popular. At the time Eddie did it, it was new to me, but now I'm realizing everybody uses adaptive boosting. So it's like a whole chapter, and I missed the whole saga in my lifetime. So everybody does adaptive boosting nowadays, right? And then, of course, Eddie also found out that one round of adaptive boosting is not going to be enough. You also need to do some sort of a cascade algorithm. So you do one sequence, and then based on the information from that one sequence, repeat it again. So some sort of a cascade algorithm for doing the classification. So I'm not going to spend too much time here. So these are the typical type of Haar wavelets they use, Haar-like features they use. Typical gradient, typical contrast, typical curvature, difference between black and white, and scan it through the entire image and pick all these things. And then, based on the information from each of these classifiers, combine them and using this adaptive boosting algorithm, where alpha m, the weights that you use to combine, are computed by specifying that I would like to minimize false negatives, false positives, whatever criteria you use for image discrimination, right? So it's a very smart algorithm, and I can get into the theory, and we did some new things with this too. Did some kernels and things like that, and for doing this adaptive boosting more efficiently. So at the core of it is a decision stump, right? So each of these simple Haar-like feature, you run it through a decision stump, use it to classify either a phase or a non-phase, and then each of these classifiers get fed into this adaptive boosting algorithm in order to come up with the final classifier, y hat, right? So that's the algorithm. So in the seismic set, it becomes a little bit interesting because the seismic is a 3D volume. So you cannot have 2D Haar wavelets. You need to have 3D Haar templates and things like that. So Eddie played around with that, but the same concept. Keep the Haar templates very, very simplistic. I would like them to be even physically interpretable. How many of you have taken a seismic class? Have you? Anyone? So in Seismic 101, if they gave you a 3D amplitude data set, and the instructor says, look at this 3D post-stack amplitude data set, and tell me where you see fractures. One of the easiest ways to do that would be to compute some curvature. And when the curvature exceeds a certain value, you say that, oh, the rock cannot sustain that curvature, so there must be a fracture somewhere, right? So they use this kind of curvature information. So if you look at it at the bottom, at the heart of it, that's what we are really trying to compute using these Haar features, this curvature type information and things like that. So once you've done this 3D things. Of course, there's another problem. The training set is highly restricted, right? The only information I have about fractures are along wells, FMI logs. The 3D seismic data set is exhaustive, but the exact information about fractures is along well bores only. And there are only few wells, not hundreds of wells, right? Few wells. So you have to come up with some smart binning, windowing of the wells and things like that, so that you can create a adequate training set to do all this, adaptive boosting and things like that. So you can see that there are some windows he specifies along well bores, just so that you can get multiple data sets to do the training and things like that, right? So again, this is a teapot dome again, right? Teapot dome, exhaustive data, 3D post-stack seismic data is available, FMI log is available. It is an anticlinal structure, so you do expect fold fractures along the folds and things like that. And it is the Niobrara shale, so it's a commercial play, right? So some interest in it. And three wells with FMI log information. So here is the 3D data set. This is what it looks, the post-stack amplitude section. And the 3 wells he shows you here. And then the FMI log is available within these red boxes that he shows over here. Again, very sparse information, right? I mean, very few wells with FMI logs. And then you have to use that to train this classifier in order to identify fractures over this entire 3D volume. And so, some details of here. This is the FMI logs, and you can relate it to the kind of lithology that you observe, and it's all been done. Eddie did not have to do it. FracGeo has done the interpretation for you and things like that. He played around with many hard-like features. He converged on 11 geometries, some of them gradient, some of them curvature, and then there are 9,868 feature combinations in each window. Right? Each window along a well, that's the number of combinations that he has. And so he did all that, and here he shows you, based on this kind of very fuzzy looking image, here are the red lines are the fractures that are classified based on this machine learning algorithm, right? And if you look at this, remember that Cooper study, he tells you that this is the ridge of the fold, and here are the fracture strikes that he identified based on actual field mapping, ground mapping, right? So kind of agrees with that. It's not going to be perfect. Not going to be perfect, because you look at this. Does anything look like anything reasonable over here, right? It's very fuzzy, but then you do this algorithm and it picks up some features and things like that. Okay. All right. So I have taken enough of your time. Let me come up with some conclusions, starting from the last portion to the first, right? I'm a big fan of simplicity. So at the heart of it is simple features. Let's get some simple features. Let's use those. Let's combine those. Let's try to to improve the computational efficiency. By the way, this 3D seismic volume, after the classification training has happened, to run it on the 3D volume set takes about 17 seconds. But the classification does take about 4 or 5 hours, right? It does take time, which is what they do in airports too, right? Every time they decommission the software and they retrain it, that's a 36 to 48 hour operation before they launch it again, and then it can detect people's faces when they come through cameras and things like that. So it's a common thing about these image recognition type algorithms. Okay, then the second thing I wanted to say that, again, I'm not offering the solution to the entire world's problems. There are a lot of restrictions there that, there are scales, multiple scales of features that we are missing, possibly missing. You can do some of that rectified by combining geomechanics and multiple point geostatistics. Again, we have not combined the seismic workflow with the MPS and things like that. That's a big thing, and I'd have to find the right student to do all of that, and I don't have one right now. And then please keep in mind that, again, this comes back to my point that fractures are fractures. Fractures are always going to be interesting. Whether you're producing hydrocarbons, whether you're doing geothermal production, whether you are doing stockpiling of nuclear waste, Yucca Mountain is all about fracture characterization, right? So if you find these kind of niche areas, there is always going to be relevance for a petroleum engineer. There is no reason to go to mechanical engineering and sign up and become students there. There's enough problems in petroleum engineering to keep a lot of us occupied for the next foreseeable future, 1,000 years. I'm not even saying 50 years, right? Subsurface problems are going to remain forever, forever. Petroleum may or may not, I don't, but subsurface problems always will be there, okay? So I'm going to end there. I'd be happy to answer any questions. Okay, fire away. Come on, yes.
Thank you, Professor, for this great presentation. My question is about the house. Could you please back it up? I want to see that picture.
Yeah.
For the fracture.
Yeah. Correct. Yeah. Somebody here?
This one.
Yeah.
Sorry. As a corner, is that the damage or what?
Where?
Yeah.
Here?
So the color bar is damage. I'm not sure.
Oh, the color bar is a strain, yes. I mean, he's just outputting some variable. It's a strain type variable that software outputs for each element. What the deformation is.
Yeah. So that means so what is the unit?
So again, these are all, he's rendered it dimensionless, scaled it by the physical dimension of the model and things like that. So I will not be able to tell you exactly what the magnitude is, but it's some sort of a rendered dimension.
Okay. Yeah. And for this case, how long does it take to run?
This one takes him about 3 to 3.5 hours on, I think it was 8 cores.
Oh,
8 cores, yeah. It is expensive. It is expensive.
Thank you.
And we could not, he wanted to run it on in Microsoft Azure and things like that, didn't work. So fortunately, Penn State has a fairly good computing system, like HPC system. So that's what we use. Of course, remember, I don't know if you guys have it here, but every half an hour they'll time you out. So you have to basically sit and plead with them. My run is going to take 4 hours. Please don't kill me. They'll terminate me in the middle. Right. Yeah. Any other questions? Good question, yeah. Any other questions?
Students. Maybe while you think of one, are you going to make me ask a hard question? No,
remember, I have an option not to reply.
No, but seriously, I'm just thinking. I really enjoyed the talk, catching up.
Right.
It got me thinking about one concern with fractures. You mentioned production data history, which is dynamic, meaning there's a time component. Then there's also microseismic, that's also dynamic. How does one tie in the causal relationships for microseisms in a geostatistical framework? Does one do that? Okay. So when I was putting this talk together, there are actually 3 students who worked on this. There was a 3rd student, Manik Singh, who looked at fracture characterization using just microseismic data. Now, I'm not the world's best expert, and maybe it's very naive thinking on my part. So I'll be happy to forward his thesis. This attracted a lot of attention, even though I thought I was being a fool, right? So with Manik, what we did is that we developed a series of proxy models, surrogate models. One for fracture propagation, used based on some crack tip dynamics. Very simplistic. I mean, you will blow me out of the water saying this is not capturing this or that or whatever, but very simple model. We have another surrogate model for propagating fractures interaction with existing natural fractures. Right? So we actually model displacement at the intersection point, and then model any kind of shear that is occurring. And then using that shear information, we propagate seismic ray tracing type algorithm. So 3 different surrogate models. Why to do that? Because I was interested in using a Bayesian model selection workflow.
So I'm going to put these three proxies together. I'm going to simulate what a synthetic seismic microseismic trace would be at a well location, compare it to the true microseismic record. Of course, that's a hell of a thing, right? I mean, we have to come up with directional distances and things like that. And then use that in a Bayesian context to say that this model of the natural fractured reservoir is the most plausible given this microseismic signature. So that's a Mani Singh's talk. I initially, when he did this, and he did a great job, I was like, maybe I should not present it. They will kill me. No, I don't know enough about any of these three topics. But it's becoming very popular. A lot of people have picked on that, and they're talking about it. I'd be happy to send you the reference for that. There are a lot of good things you can do with that, but for my naive thinking, it did a lot of things to clarify things in my mind. So it's a very intriguing problem, and there are a lot of other people, right? I mean, you do some fantastic things in that, right? And there are other people. Mark McClure has got some very nice approaches for that, right? And they're developing that. And Pallav also talked about some approaches for that. Yes, but there is some geostatistical.
But do you think microseismic data can inform of hydrodynamics?
No, I'm not doing this.
Isn't the hydrodynamics the cause of the microseismic?
I know, but the sampling frequency of the microseismic is very, very different. The sampling frequency is still not to that level to capture the true dynamics. Now, of course, you can argue them. They do that all the time, right? They do trajectory modeling and for plausible trajectory modeling within discrete time limits. There's a lot of theory for that, and maybe you can do that. But raw microseismic relating it to dynamics, I would be a little bit nervous about. I'll be a little bit nervous.
Good. So last question.
Yeah.
Given that there's basically, if we take that as fact, there's no hope really in ever really, utilizing microseismic to connect us to the production data assimilation side of things, because then the two are in different worlds.
So my happy medium.
Microseismic here, you're talking production. How do you reconcile?
So my happy medium is shut your mind to the dynamics treated as static information.
Yeah, quasi-static. Because you can always, update that.
Think like an engineer. Right, and so you do all those quasi-static, and your saving grace is that every 2 years you come and revisit your model. Any other questions? Come on, guys. How's life? Finals coming up for semester? Next week or after December? Any tips for exams? This exam that I use.
So we've got drillers, we've got production engineers in the room. Yeah. This is, we don't really work with geosciences as much.
By the way, I will say this, in close group project. Geoscience folks, if you notice, are no longer enamored with rocks. They will do anything but rocks. They will talk about climate. They will talk about, chronological sequencing of data. Right? Rocks is not their favorite thing. Right? At least at Penn State. You will be hard pressed to find a geology professor who will teach you petroleum geology or sedimentary geology. They don't like that. That's too simplistic. Talk to me about geochronology. I can do that. Yeah.
Dr. Srinivasan. So I know very little, almost know nothing about geomechanics, statistics, and also reservoir. So I don't have good question, but a stupid question probably. I was wondering for fracturing, and either you do the fracturing or you do the modeling. Can you eventually reach to permeability? So you, I mean,
Yeah, I mean, it's a tricky question. Some time ago, reviewed a report for Schlumberger, right? So I know most of you know there's a scheme by ODA looking at permeability of fractured media, equivalent permeability.
right.
A whole can of worms, because you make all kinds of simplistic assumptions about periodic boundary conditions and all these kinds of things. So it's a you hope, but you're not there. And definitely not there until people like Rami come up with new generation of simulators. Definitely not there if you discretize your reservoir into grid lines, because these structures trend across multiple grid lines, and then there is no closed permeability you can assign. So I think what you're telling me is all this is great, but is it ever going to be used?
Right.
That's a good question. That's a good question. That's a good question. That's a good question. Yeah.
From the reservoir simulation side of things, what we'll use is take an image like that and then assume Poiseuille flow in the
Yeah.
ground.
Okay.
So the thickness squared, the aperture squared is the parameter.
Right.
But that's like
That's why they resort to permeability as a history match variable, and at the end of the history match, it doesn't relate anything to the fracture. It doesn't say anything about the fractures. It's a lot of it. But you see, the very fact that we are talking about this, doesn't it impress upon you that the challenges are enormous? We are taking baby steps right now. Right? The challenges are so enormous. I hope, despite your final exam schedule and all, you relate to that. That we are all in this because we are passionate about things, right? And it should be the passion. Small things, if you solve, big becomes big. Big. Yeah. All right.
Let's thank Dr.
Thank you for taking the time. And if you want to get any more details, please do email me. I'm happy to chat. Anything you want, any of these dissertations, I'll be happy to email you if you're ever interested. If you just want to talk about life in general, email is available, right? Okay, you can solve to me, I can solve to you. Okay, all right, good, thank you. Did I go too much over time?
No, perfect. I'm just going to stop the recording. Really nice.